So today we will be discussing about the closure properties of regular languages. Now what do you mean by closure properties? So as we say that language is closed under some operations. Okay. So I hope in discrete mathematics as well you must have come across this terminology. Okay. So we will be discussing the closure properties of regular languages in this lecture. So what are the different closure properties for a regular language? So it is mentioned like this. The principal closure properties are very first, it is the union of two regular languages is regular. Now what this means? So suppose I am having a language L1, okay, which is represented by some regular expression. For example, I'll have any regular expression R1 as suppose A star. I'm having another regular expression, for example, B star. Okay. Now my language will be empty A, 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 dash, 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 right? Similarly, my L2 will be L, regular expression R2. So now it will be empty, A, B, 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 dash, 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 right? Now, if I am saying that this is a regular language, this is a regular language, then union of L1 and L2, will it be also regular? Whether these two regular languages are closed under union operation. So whenever we are saying the union of this L1 and 2, L1 union L2 will be what? It will be nothing but the empty will be there. Now all the strings here and all the strings in this set both will be in a resultant union set. Agree? So empty is common. So all A, dash dash comma B, 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 dash dash dash, right? So this will be my resultant set of L1 union L2. Now if I want to represent, suppose this is my L set. If I want to represent this L set with any regular expression R, then what it will be? How you will be representing this R, just like I have represented R1 as A star, R2 as B star. Now how I will represent the regular expression for this set. So what is this set? It is having all the strings which is coming in any combination, right? So what will be the expression for this? Can I say R is equal to R1 plus R2? Now since it is a star, can I write the star here? If it is a star, then anything can come and concatenate with it. So I cannot write. So here union is nothing but my plus sign. Okay. So it is A star plus B star. So whenever we are writing A plus B, remember when we have represented any regular expression as A plus B, that time we have represented a language as this set is having A as well as it is also having B. So this was our set, regular set corresponding to this particular regular expression, right? Similarly, here I am unioning these two sets. So my expression will be R1 plus R2, that is A star plus B star, right? Now, can I say this A star plus B star is representing, can I write regular expression for this set? Yes, I can write. It is what? A star and this is a B star and both are there. So it is nothing but represented by A star plus B star. So if any language which can be represented with the help of a regular expression, we call such a language as well the regular language. Agreed? So from this observation, from this example, what you can say, if L1 is a regular language, L2 is also regular language, therefore the union of the two regular language is also a regular language. Okay. So likewise, we have to find out. So this is one kind of explanation regarding how you will be proving that the languages, regular languages are closed under the union operation. So what are the other operations under which the regular languages are closed? We will now discuss. And I will share the proof PPT to you for all these closure properties. So very first I have already discussed. So the union of two RL is also a regular, right? That is if L and M are two regular language, then so L union M so is L union M. This is a first closure property. Similarly, second is the intersection of two RL is the intersection of two regular language is also regular, right? So again we have to express if L and M are two RL, then so is L intersection M. Third property is the complement of two RL is again regular. So if L is a regular language over summation, then summation star minus L, okay, is also regular, right? Fourth, the difference of two regular languages regular. So difference of two RL is regular. So again, if L and M are RLs, then so is L minus M. Next, the reverse reversal of RL is regular. Okay. So what will be the reversal of a regular language? So if your L is equal to suppose 001 110, then the reversal of this language will be 100 or 011 will also be a regular. Okay. So if L is a regular language, then its reversal is also a regular language. Next, sixth is the closure property. Next closure property is the closure. So the closure of a RL is regular. That we have already seen number of times. So if L is RL, then so is L star. Next is the concatenation that we have already seen during the definition only of RL is regular. So if L and M are RL, then so is L dot M, right? Now next is the homomorphism. Homomorphism of RL is regular. Now what do you mean by homomorphism? So, homomorphism, for example, if we are having any string, so it is just a substitution. So a homomorphism is a substitution, right? So homomorphism is a substitution of string for a symbol. Okay, for example, and it is represented by the h function. Okay, so let the function h be defined by h of 0 is equal to a and h of 1 is equal to b. Then h applied to 0011 is simply what? AABB. So after replacement, what will happen? You will get the this language. So the language generated after the homomorphism or substitution, still this string will be satisfying the condition for being in a regular language. Okay. So this is, so if L is a regular over, so finally we can say if L is a regular over our over summation and H is a homomorphism function on summation, then H of L is also regular. So I hope this is clear. And ninth is the inverse homomorphism. The inverse homomorphism okay, of RL is also regular. Okay, so same way you have to express. So suppose that is a homomorphism for alphabet of string. So suppose H be a homomorphism from some alphabet to string in another alphabet T, and L be a language over T, then H inverse of L, which is represented as H dash L, is set of strings W in summation star such that H W is in L. So I hope you have understood. So the theorem states that if the H is a homomorphism from alphabet, okay. So what is the theorem says? If H is a homomorphism from summation to capital T. See, both are the alphabets, and L is a regular language on T, then H inverse L is also a regular language. So I will be sending you the PPT related to it. So I hope this is clear to you. What are the different closure properties? So different closure properties. So the regular languages are closed under union, intersection, complement, difference, reversal, then closure, then concatenation, then homomorphism, and finally it is also closed under inverse homomorphism. Okay. Now I hope you have understood it. Now we are discussing the next point, that is the decision properties of regular languages or regular sets. Okay. Now, why these properties are called as decision properties, as its name suggests, decision. So what decisions we want related to the regular languages. So how we will represent now with this? So there are three decisions we want. First decision is whether the given string is belonging to the finite automata, or whether the language generated by the finite automata is empty or finite or infinite. Okay. So when we will say a particular regular language is empty or non-empty, finite or infinite, so you will express this like this: the set of sentences accepted by FA n having n states is, for first, non-empty if is empty, if and only if. When you will say that the language generated or strings generated or accepted by finite automata is represented here M, which is having N state, is non-empty if and only if the FA accepts a sentence, or you can say string, whose length is less than n. If the string accepted by finite automata is having length less than n, where n is number of states, then we say that the language is non-empty. Otherwise, when you will say it is empty, if it is having zero length, right? So that time, so zero length empty string is also giving you what? It is a acceptance, for example. Okay, if the initial and final state are same, single state, okay, then your finite automata is accepting a empty string. Don't forget this. Okay, so if initial final state are same, and then in that case there is no self loop even, then also your finite automata is accepting an empty string. And we have just discussed in the regular expression that even empty string is also a regular expression. Even phi set, that is empty set, is also representing a regular expression. So if it is a regular expression, then language accepted by any finite automata which is generating empty set, that is also a regular. Okay, next is when we will say infinite. So infinite if and only if the FA accepts some statements whose length is L, where n is less than equal to L, less than equal to less than 2n. So again, what do you understand it with this? So we have seen many infinite languages. So what is a simple way to understand infinite language? If self loop or some kind of loops are available in a finite automata, so it clearly indicates that it is an infinite language. I hope everybody agrees. Now, when we have discussed the pumping lemma, that time I have told you, if your finite automata is having n states, so minimum string which is acceptable by that finite automata is n minus 1, right? Without any loop. Okay, so for n state, we can have acceptance of a string which is having size n minus 1. Now here what we are saying, when it will be declared a language as an infinite, if it is having length equal to, okay, less than equals to n. L is a length of string which is greater than, see L is here, so L is greater than n or equal to n. As soon as it is equal to n, it indicates clearly that there will be some kind of loop, because otherwise if no loop is there, the minimum string accepted will be n minus 1, and it is greater. So all the strings having size n and greater than n and which are less than 2n. So this you need to remember again. You will see the proof by only 2n, not more than that. Okay. So if the case is like this, that the language strings are having length which is greater than equal to n and less than the 2n, then such languages are called to be the infinite languages. Otherwise, the languages are the finite language. So what decisions we are getting? So if you give any input and you will ask, you want a decision, whether this finite automata will generate the uh, empty set or non-empty set. Okay, is it a empty or non-empty? So how you will prove? You will prove it with that if it is having at least a single string, empty string, or it is having initial final state, then it is accepting some string which is having size less than n, 0, empty, or less than n. And if it is infinite or finite, whether the given language is finite or infinite, so it depends on what is the size of the different strings in the given language. So if you can generate more number of strings with this particular condition, where this is not satisfying, n minus 1 only states are not required, then in that case you can say it is a infinite. So what are the different decision properties of regular language? So there are whether the string is, the language is representing a emptiness or finiteness or the infiniteness. So emptiness means if no strings are generated, finiteness if the limited number of strings can be generated by the finite automata, and if you can generate less than equal to, greater than equals to n and less than 2n size strings from the finite automata or accepted by the finite automata, then we say that it is a infinite language. So with this, we have also discussed the decision properties of a regular language.